have... So, okay, here we go. Moving forward. For the rest of this discussion, let's assume that we used parallax or any other method available to astronomers to find the distance. So let's assume that we know the distance for every star out there for the rest of this discussion, okay? All right, the next property that's important is how bright stars are, okay? And the thing that we're going to use to talk about how bright stars are is a property called luminosity. And here you can kind of think of the lumen part as meaning light, right? So luminosity is, it's the total amount of light produced per second, okay? The total amount of light energy, here we go, total amount of light energy produced per second. Okay. Total amount of light energy produced per second. It's the total light that a star is sending out in all directions per second. Okay? Now, two things here. Let's figure out if this is direct or indirect, and let's figure out what the units of it are. Okay? Let's first say direct and indirect. Okay? Let's first talk direct and indirect. Check it out. Here we go. Let's take a vote. Is the total amount of light produced per second something that is direct or indirect? Are we going to be able to directly see that, or is that something we're going to have to figure out? Take a vote in the Discord while I adjust some things here. There we go. Okay, I'm getting some votes coming in. Let's see where we're gonna put it. Okay, I'm getting multiple answers here. Let's see what it is. So most of you guys got it, and it's okay if you didn't get it. A lot of times people think that this is direct, but it is indirect. Okay, I'm going to go ahead and write it down, and I'll explain why. And we use a capital L for luminosity because a lowercase l looks like a 1. We don't want that, okay? So, why is luminosity indirect instead of direct? So it sounds like the total light coming out of a star per second is something we could measure. But we can't, because which direction does a star put out light? Which direction does a star put out light? All directions. So if you were going to measure the total light that a star put out in 1 second, where would you have to view it from? If in order to catch all of the light that a star put out in that second, where would you have to view that star from in order to get a direct measurement? Yeah, you would have to be on all sides of the star. Essentially, what's the problem is this. Oh, come on. The problem is that the star is putting out light. Come on, you can do it. One moment. Technical difficulties again. This is just killing me. Okay, let me reload. Come on, you can capture it. It's not wanting to capture my my PowerPoint presentation anymore. Okay, so give me one moment. We're gonna do this a very clunky way. Here we go. This final stream, guys, it's working out really well. Final try. Please work. Please work. Sorry, guys. Okay, here's how it's gonna have to go. There we go. Okay, so I'm back. Sorry, guys. Here we go. Now, here we go. So, I've just got this open over here. I'm just gonna have to show you guys the full screen. Like we were saying, the problem with luminosity is that the total light goes out in all directions, okay? So the light is coming out like this, and we're only able to catch the stuff that hits us. We could probably assume that the light going in all directions is the same as the light coming at us, but that's still indirect, because we're not for sure that the light coming out over here is exactly the same as ours. But because this is a ball-shaped star and the star is pretty uniform, we expect that the light going out in all directions is the same as the light coming at us. So how do we distinguish all of this? So essentially, sorry, this kind of threw me off my flow here, but I can get this. Essentially, we need to make a distinguishment between, is that a word? Whatever. It's a word now. Here we go. We need to distinguish between the light going out in all directions and the light that's hitting us. So we call the light that goes out in all directions the luminosity, and we call the light that hits us the apparent brightness. Okay? The apparent brightness. So let me pop back up the lists. We're going to put apparent brightness over here in the direct pile. With a lowercase b. And we're going to leave luminosity over there. Okay, so again, luminosity is the total light it sends out in all directions per second. And the apparent brightness is the stuff that hits us. Now, those two things are related, okay? Because if the luminosity of a star is higher, if it makes more light per second in all directions, what will that do to the apparent brightness? If the star makes more light in all directions, what will it do to apparent brightness? If the luminosity is higher, what happens to the apparent brightness? You guys still here? It would be higher. That's correct. It would be higher. So if the star makes more light, it's going to look brighter, okay? But the apparent brightness, the brightness we see, is not just related to the luminosity. It's also related to one other important thing that we've already listed, okay? What else on our list is the apparent brightness going to depend on? The distance, right? Right? You probably learned as a little kid, if there's like a light bulb on, do you want to put it way up in your face? No, because that's going to make it look way brighter and it's going to hurt your eyes. If you go further away from a light bulb, it's not going to be as bright, and therefore it's not going to hurt as much. So that means the apparent brightness depends on the luminosity and the distance. If the luminosity goes up, the apparent brightness goes up. But if the distance goes up, if the star is farther away, it's going to look dimmer. So that means the apparent brightness will go down. Okay? Everybody good? All right. Now, what we have to get here, though, is this. Why? Like, everybody knows that things that are farther away look dimmer. Why do they look dimmer? Why is it that stuff looks dimmer when it's farther away? This is a hard question, so give it a try. See if anybody can figure it out. Why is it that things that are farther away look dimmer? And I'm going to give you guys a hint. I'm going to bring up my PowerPoint again. This picture will help you answer it. So it's definitely that less light gets to your eye, but why? Why does less light get to your eye when you go further away from this star? Oh, somebody is saying that the gases between you and the star would absorb more of the light. Well, remember, space is mostly a vacuum, so this works. Things that are farther away are dimmer even when there's nothing between you and that object. Somebody got it. Looks like somebody got it. What's happening to this light right here as it goes away from the star? What's happening to this light? So if this is the amount of light it made per second, what's happening to that light as it goes away? It spreads out. It spreads out. So you're looking at less and less of it by the time it gets to your face. Somebody described this in terms of angles. That's basically right. Essentially, imagine this. Let me kind of get myself kind of small. Here we go. If I were looking at this star from here, see how a bunch of the lines are crossing my face? I would see all of this light, right? And if I go further away, see how less lines are crossing my face now? Now I only have 3 crossing my face. And if I go further away, now only 2 are crossing my face. And if I go even further away, eventually only 1 will cross my face. So because the light spreads out as it goes away from the star, you're catching less and less of it. You become a smaller target as you go away, so you catch less of that light. So it's a spread. Because the light is spread out on the surface of essentially a ball, you end up missing more and more of it the farther away you go. Okay? Now, here we go. Looks like somebody has a question, so I'm going to brief pause for that to come in. And then I'm going to switch over to this. I'm going to show you guys an equation that says what we just said. Okay, let's get this down. This is not part of our lists. I'm just going to put them over here. Here we go. The equation is this. B equals L over 4 pi d squared. B equals L over 4 pi d squared. Okay, let's see what this means. Don't freak out. You're not going to have to plug numbers into this equation. You're not going to have to do math like that on a test. You're not going to need a calculator. We just need to see what this equation says. Now, just to make sure, if we look on here, check this out. This over here is our apparent brightness. This up here is the luminosity, and that's the distance squared, okay? But what is this saying? This is a fraction right here. And if we wanted to be really super fancy, we'd call the top a numerator and the bottom a denominator. But let's not get super mathy and crazy here. Let's just call this the top part and the bottom part, okay? If we have a fraction and we increase the top part, what happens to the total? If we were to increase the L here, what would happen to the total we would get if we were to actually calculate this? If you increase the top of a fraction, what happens to the total? Does it go up or does it go down? It increases. It increases. So one thing this equation is saying is that... Wait, I'm losing something. There we go. One thing this equation is saying is that if we increase the luminosity, it's gonna look brighter, which is what we said before, okay? but distance is in the bottom part. If we increase the distance, if we increase the bottom of this fraction, what would happen to the total? If we increase the d right here, because it's in the bottom of the fraction, we're making the bottom of the fraction bigger, what would happen to the total? It decreases. It decreases the overall total. So in other words, if you make if you have a fraction and you had like a 1/2, and then you made it a 1/3, and then a 1/4, you're making your total smaller by increasing the bottom of the fraction, okay? So anytime we have something like this, if we increase the top, the total will go up, and if we increase the bottom, the total will go down, okay? Now, what is this 4 pi d squared here? Geometry is not a prereq for this class, but does anybody know what this bottom formula is for? 4 pi, let me say it in a different way. Have you ever seen the formula 4 pi r squared? That is the formula for the surface of a ball, okay? It's the formula for the surface of a ball. And remember, in the picture, I said that the light of the star, the luminosity of the star, is spread out over the surface of a ball, right? So that's why the equation for the brightness you see is the luminosity over the surface of a ball. So it's kind of putting into an equation the words we were saying, okay? Let's put this all together. There's a reason I'm putting this here. Remember, if an astronomer is trying to figure these properties out, they've already found the distance. So in this equation, we already know d, right? Is the astronomer going to have to use this equation to find the apparent brightness, or are they going to use this equation to find the luminosity? Is this equation for finding the apparent brightness or for the luminosity? It's the luminosity, right? Because the brightness is what you see, okay? The brightness is what you see. So that means that we don't need to use this equation to find B. So what I'm going to do, don't freak out, I'm going to do some quick algebra here. Check it out. If we solve this for L, I would do that by taking this bottom part and multiplying it over to the other side. Remember, you're not going to have to do algebra. This is just for us for now, okay? So check this out. If I multiply that to the other side, I get 4 pi d squared b equals L. So that means when an astronomer wants to know the luminosity, the total light of a star, they're going to use this equation, okay? And if they want to use this equation to find L, here is a possible test question I could ask, okay? If an astronomer wants to know the luminosity of a star, what 2 things do they need to know first? Put it in the Discord. If the astronomer wants to know the luminosity of a star, what 2 things does that astronomer have to find first? Distance and apparent brightness, okay? So I could ask you a question like this. I'm not going to ask you a question where you have to write this equation out or actually plug it in, but it does tell you how these things are related to each other. If you need this, then you have to get the distance and brightness to get it. Does that make sense? So if I asked you that question on the test, distance and apparent brightness would be the answer, okay? If I asked you that on a test. Woo! Okay.